Okay, so this video is supposed to be an explanation of a problem that I got in a discrete math course that I'm taking at IIT Gandhinagar. And I'm making this specifically because this I cannot put in words. I need like some pictures to show the method easily. And also because I'm not formalized it yet, so I don't know how to put it. Um, but here goes nothing. So the question is that suppose you have some friends and not all of them are necessarily friends. So you have friends like these, for example, and there's a rule that any two people, friend or not, must have odd number of mutual friends. So suppose these are the friends represented by the nodes, then uh, two friends A and B must have an odd number of mutual friends, that is friends who are both, so people who are friends of both A and B, right? So for example, over here you have three mutual friends of A and B, and this is supposed to be true for any two pairs, so any two nodes in this graph, right? And what we want to prove is that the number of nodes is even. Okay, so let's go. First of all, before proving that, I'm going to prove something which I think is stronger than that. I don't know why I was unknown to this fact, but so the thing is, like, you have a node A. Let's partition the whole graph into two sets. So you have a set FA and a set F dash A. So FA is all of the friends of A and F dash A are all of the non-friends of A, that is friends, so that is people who are not friends of A. So A is connected to every single node over here, and I'm not going to show these arrows. Okay, so for any node B inside of this, since A and B, you can take these as two pairs, and let's just use small a over here, so small for nodes, right? So A and B, they must have an odd number of mutual friends, but then if something is a mutual friend of A and B, it's of course a friend of A as well, but that means it lies in this set FA. So we are looking for all the nodes who are friends of P inside of FA, and we are seeing that those nodes are odd in number, that is B has an odd number of connections inside of FA. This can also be said as the degree of node B inside of FA. If you consider this as a graph, that is odd, but then by the handshake lemma, I think that's what it's called, what we have is that the sum of these degrees over all of the nodes in FA, that must be 2 times the number of edges, so that's an even number. But what that means is that the number of nodes in FA must be even because you're adding up a bunch of odd numbers. So what we just proved is that any random node, so any arbitrary node small a, that has an even number of friends because the cardinality of f sub small a is even. Okay, but we can do a similar analysis for some node inside of f dash of a. So suppose we have the node C over here. We know that C and A must have an odd number of mutual friends. Once again, any mutual friend should lie in FA because it's a friend of small a. So what that means is that C has an odd number of connections inside of FA. But we have just proved that any node has an even number of friends, connections. But what that means is that it must have an odd, so C must have an odd number of connections inside of F dash of A for the total number of connections to be even. So there you go, right? So now let's just forget about this completely, its connections with the other elements, and let's just focus on F dash of A. So every node inside of F dash of A has an odd number of connections inside of F dash of A. That is, if you consider the graph that is only using these nodes, so forget all the other edges, all the other nodes as well, then the degree of any node over here that is odd So once again, by the similar logic that we did for fa, we can prove that the cardinality of f dash of a, that must be even. So combining all of these facts together, you have even plus 1, which is an odd number. So there you go. We just proved that this whole graph has an odd number of people. And yeah, that's it. So I did a somewhat incorrect proof at first for this, and I want to show why that is incorrect, because I explained this to my professor and she said look at the base cases, and indeed my base cases were wrong. So it's something like this. Suppose you have a graph, any general graph, and this is the weird thing that I did not use the original property of odd number of mutual friends at all. So this is like some kind of induction that applies to all graphs. Yeah, so where was I? Right, this is some graph that you have. What was I going to do? Right, you take two people who have the same parity of number of friends, right? So let's still forget all of this. You take A and B, and they have the same parity of the number of friends. Then you look at the, how should I draw this? Just draw two circles. So you look at their union except the intersection, right? So since they have the same parity, we know that these areas, so these contain, so like this is, you can think of it as FA, and this is FB, where FA is all of the other nodes other than A and B, right? This whole thing, by the way, this whole circle, which are friends of A, and similarly FB is all of the people which are friends of B except A, of course. So since they have the same parity, FA and FB, they have the same parity, because even if they are connected, you go from even to odd or odd to even, right? And if they are not connected, then FA and FB are exactly the number of friends that A and B have. Okay, so now their intersection, you can remove that from FA and FB, and then once again, since you remove the same thing, their parities are still the same. So what that means is these shaded areas, they have the same parity, so their sum is even, right? And now what we can do is we can break all of the edges connected to A and B, basically remove the nodes A and B. So if you had a whole graph G, what I'm looking at is G minus A minus B, right? So everyone over here in the intersection, they have two edges going to A and B, those are removed. So the number of friends of any node C inside of the intersection, that is still the same parity as before. So the intersection doesn't have its parity changed at all. For the shaded area, you take any node inside of this shaded area, it is connected to only one of A or B, which means that it changes its parity. So the thing is, since the shaded area has even number of people, there are even number of people who change their parity, but that does not change the number of people who have odd parity or the number of people who have even parity. Because what could happen is that, okay, odd number of people went from even to odd, but that would mean that odd number of people also went from odd to even. So the number of people who had odd parity, that's still the same as before, because odd minus odd is even. And similarly, the number of people who have even parity, that's still the same as before, right? So we broke all the edges, and this is what happened. Now we can also remove these A and B, and then once again, everything over here, it has the right, yeah, the remaining graph, it still has the same parity for the number of people who have odd parity as before. So it's a bit of mouthful, I'm going to write it down. So the number of people with odd or even number of friends, and we want the parity of that. So parity of this thing is the same as before, right? Yeah, and I spent a lot of time explaining to her what I'm doing. So this is what I'm doing basically, this thing. What I did was I just did G minus A minus B, right? Where A and B have the same parity of number of friends. Yeah, so now you have two less people in this new graph. So suppose your graph had n people, now you have n minus 2. We can do an induction on n minus 2 and keep removing such nodes. So we just cross these out. Now these are not in our graph, the graph we are considering. And we just keep doing this until all of the people have different parities, right? And the only way that this could happen is if n is less than 3, because if n is more than 3, there will be at least two people with the same parity by the pigeonhole principle, since we have two categories, right? So the only numbers less than 3 for the number of nodes, sorry, it should be less than 2, right? Because, well, okay, so the case for 2 is slightly different. So for 2, okay, no, actually, I mean, fine. So it could be that you have two people with odd and even parities. I mean, they have different parities in two categories. So this is where the pigeonhole principle is not, spoiling everything. But then, of course, it by itself is getting spoiled, because if this has odd parity, it must be connected to something. And the only thing it could connect to is this. But then this also has odd parity. So how is it even? So this is just impossible. So the only cases we are left with is if there is a single person inside of a graph and if there's no one. So if there's a single person, then the number of odd people is even, and the number of even people, I'm talking about even people and odd people, it's odd. So people with odd number of friends. That's what I mean by odd people. So the number of odd people is even, since it's 0, and number of even people is 1. So since we can, since removing A and B with the same parity does not change the parity of this thing for both odd and even, we know that the original graph also has even number of odd people and odd number of even people. And this is where we need to pay attention to the base cases, because this is only one base case. So that's when n equal to 1. But there's also another base case which I completely forgot about, and that's the n equal to 0 base case. So if n equal to 0 base case was not there, you basically have just proved that any graph has an odd number of people, sorry, an even number of people with, okay, that is already there. Oh, right. So over here you have one person, and in every induction step you are removing two people. So what you have just proved is that any graph has an odd number of people, which is wrong. It's of course wrong. So by this reduction, like by removing these two, we are reducing the graph. If you keep this on, so if you keep reducing this, you must end up at this, or, so the thing I forgot was if there's no one in the graph, right? Because then the number of odd people is 0 and number of even people is 0. So that is still even and even, which is the same thing as, the original graph, right? That's another base case. But then of course number of people in the original graph is not odd, since over here you have 0 people, so 0 plus 2, then plus 2, and so on. So that's an even number, right? So n would be even. So yeah, that's all I wanted to say. Thank you and have a nice day.